Thank you. Thanks for the invitation to the program and the boot camp. So I'm going to pick right up where Daniele left off, talking about SIS, to talk about the learning with errors or LWE problem, some applications, and also an outline of the hardness proofs for LWE. So just like SIS, where Daniele showed us this worst case to average case reduction, there's also such a reduction for LWE. But it's more involved and a little more subtle, and there are some nice open problems related to it. So let me just say at the outset, please feel free to interrupt. Raise your hand, ask questions. I prefer to get a lot of questions, and I think I have time, plenty of time for elaboration. Okay, so this is the outline. We will recall SIS, which was done an hour and a half ago, so you might have forgotten some things, and then we'll introduce LWE. And then we'll talk about a few cryptographic applications, and then we'll talk about, at least at a high level, the proof of hardness of LWE. Okay, so first we'll define learning with errors and give some perspectives about how it relates to its counter problem SIS. Okay, so let's just do a reminder from 2 hours ago or so. The SIS, or short integer solution problem, first defined, but I think not named by ITI in '96. So the problem has two main parameters, a dimension n and a modulus q. And you can think of this q as being relatively small, maybe a small polynomial in n is just an example of a typical choice. And we're interested in looking at the set of n-dimensional vectors of integers with mod q entries and mod q operations. So the SIS problem is as follows. The challenger gives the SIS solver, or the attacker, several uniformly random vectors from this ZQN domain. Okay, so some large number of them, m. And the challenge is to find, given these uniformly random vectors, find some non-trivial small combination of them, integer combination of them, that adds up to 0. Okay, so we're looking for small integers, z1 through zm, that are not all 0. Okay, all 0 certainly works, but we want a non-trivial set of numbers. So a non-trivial set of small integers such that this sum adds up to 0. And all the arithmetic here is modulo q. Okay, so each of these vectors, maybe we take one of these and two of these and negative one of these, should add up to 0 mod q. So that's the goal. We can write this a little more compactly as a matrix and vector multiplication. Okay, so if we take these columns, A1, A2 through AM, and just bunch them up into a single matrix A, then we have a matrix which is height n and width m. And then we're looking for short non-zero vector z, such that A times z is the all zeros vector on it. So this problem would be easy if not for this short requirement. Okay, so you could solve this problem easily just using Gaussian elimination. But it's going to give you a very large vector z whose entries are roughly q or so, q over 2 maybe. But we're looking for a vector, all of whose entries are very small. So that's what makes this problem more difficult. Okay, so that's SIS. And as Daniele showed you, there's a collision-resistant hash function that we can get from this problem, or assuming that this problem is hard. So if we just take this matrix A as the uniformly random key to the function, and then we define the function f of x as just a times x. Okay? And the domain here is binary vectors, so 0, 1 vectors of dimension m, and then those hash down to a vector in ZQN. So the domain is larger than the range exactly when m is larger than n log q. Okay, so this is a compressing function. And it's collision resistant. So what this means is if you can find a collision in this function for a randomly chosen A, then you can break SIS. Right? And how do we do it? Well, if you've managed to find such a collision, so that's an x and an x prime, which are different from the domain, where ax equals ax prime, then just subtract. Okay? So you subtract, and you get x minus x prime. This is a non-zero vector. All its entries are 0 plus minus 1. And a times this z equals 0, just by the fact that ax equals ax prime. Okay, so this should be a review from last time, but any questions or reminders about this material? Okay, great. So that's kind of the first application of SIS. So it is useful also to look at SIS itself as a lattice problem. And to do so, we imagine taking this matrix A that we had before, so this uniformly random matrix A, we define an object called L-perp, or the perp lattice or orthogonal lattice of A is just the set of all vectors, integer vectors Z, such that AZ equals 0. So this is defined without regard to the norm of Z, right? So this includes long vector Z, short vector Z, everything in between. So it looks something like this. And a few easy observations about this lattice are that it's it's Q-ary is the term for it, or it's closed under shifts by Q. Okay? So this point here, 0, Q, and Q, 0, these are points in the lattice, just because Q times anything is 0, mod Q. And this corner of QQ is as well. And if you just look inside this box and you shift the box, by Q in any direction, you get exactly the same thing. So the lattice is kind of periodic modulo Q, but all the interesting stuff is happening inside of this box. So that's the lattice, the L-perp of A. And you can think of A as like a parity check matrix. If you're familiar with coding theory, the term for A here is parity check matrix for the lattice. So what is SIS asking for? It's asking for a short solution, or that is a short non-zero lattice point, okay, in this lattice. Right, so given A defines this big lattice with all these points all over, and the goal of SIS is to find a short vector in this lattice, so something within this radius around the origin. So that, in this way, we can see SIS as like an average case short vector problem on these kind of random lattices. One other concept that we'll need is the idea that there's also cosets of this lattice. So here's the lattice with the origin included, and then we can shift the lattice maybe a little bit to the left, or up and down, or however you want to move it. If you shift the lattice, that corresponds to a coset. And we use this notation here. So L-perp sub U, this is just the set of all integer vectors where AZ equals U. Okay. So U equals 0 is the actual lattice. But if you choose some non-zero U, that corresponds to a non-zero shift of the lattice. And that can be seen as just the set of the original solutions plus a particular solution. Okay, so the homogeneous solutions plus a particular solution all have the form where U equals A times T. So that's a coset, and this would be called like the inhomogeneous SIS, or ISIS, as I like to call it. Okay. It was before the recent unpleasantness. Before the recent unpleasantness, yeah. And
HSIS for the homogeneous SIS.
HSIS and ISIS?
Still,
okay. I mean, ISIS goes back to ancient Egypt, right? It's only lately been soiled. Okay. Okay, so that's the inhomogeneous problem, the homogeneous problem, whichever you like is what you can use. Okay. So what we have here, which Daniele showed us, is this remarkable worst case to average case reduction for SIS, which says that there's a reduction where if you have an algorithm to find short non-zero vectors in this lattice, or even in a random coset of this lattice, for a uniformly random A, then you can use that algorithm to solve various lattice problems in the worst case. Okay, so on any n-dimensional lattice. And there's some quantities here that are important. So the bounds that we need is the length of the vector should be at most some bound beta that we fix in advance. And beta should be substantially lower than Q. Okay, you can always find vectors of length Q, like this one here. Okay? But if you fix beta to be substantially less than Q, then finding lattice vectors of that bounded norm is as hard as approximating lattice problems to factors roughly beta times root n. So there's this root n kind of slack, I guess, between the length of the SIS solution and the approximation factor. But typically, we set beta to be some small polynomial in n, or maybe just a bit more than a polynomial. But in any case, these approximation factors are very hard to attain using our known algorithms. So this is the nature of SIS. It's really remarkable because it says if there are any hard instances of these problems, then this problem here is hard for uniformly random choice of matrix A. So you can actually generate hard instances by just sampling them at random. Okay, so any questions about the SIS review so far?
Chris, this is just the one-shot reduction, right? If you iterate.
No, this is the iterative one.
But SIVP, the factor depends on beta.
Huh? Yeah, they both depend on beta.
Think of the last step of the reduction. Forget about all the iterating.
Yeah, this is the iterative reduction. The one-shot reduction would be much worse in choice of Q.
Yeah, it's best.
Okay, so that's the SIS review, and just kind of, yeah.
So in terms of SIS, so the shaded circle should actually be bigger than the square.
Yeah, the figures are not drawn to scale here. Yeah.
Some previous questions this morning about the density of the lattice and to put it in scale.
Yeah. So I wish if we had like a 100-dimensional board, I could show better pictures. But just one thing to note is like this point here, is -2, 1, and 2, -1, right? Normally you'd have a lot of lattice points inside of this ball.
But you can also pick, if you make the ball bigger, right?
Yep.
Then you get multiple solutions and you get one.
Yeah, that's right. But any even reasonable size of a ball will have a lot of solutions in it, not just 2.
This would be LWE, correct?
No.
It's not a determinant
Yeah.
of the lattice, the big square, right?
Yeah.
Okay, no, then it's fine.
Yeah, this is
the way it is.
morally what SIS looks like. Here. Okay. So now let's flip the page. Flip over to. In fact, it's kind of the other side of the same coin to talk about LWE. Okay. So LWE was introduced almost 10 years after ITI by Regev in 2005. And just like SIS, it has the same parameters, N and Q. Again, think of Q as polynomial. It doesn't have to be, but it's most useful to think of it that way. And it has one more parameter, which is an error distribution. So the error part is new here. And here is the problem. Okay, so there's kind of 2 flavors of LWE. There's search and decision. So let's tackle search first. So the idea of search is that there's a secret vector S in ZQN, and the attacker is given many random noisy inner products with S. So what does this mean? Just like before, we have these random A1, A2, A3, up to AM. Okay, these are chosen uniformly from ZQN. And then we give the attacker these A1, A2, and so forth. We also give the attacker S inner product AI. Well, not exactly. We don't give it exactly S inner product AI. We give it SAI plus some noise. Okay, and the noise is drawn from this error distribution here. So a little more precisely, it's BI is S inner product AI plus EI, where the EI is drawn from the error distribution. And the typical error distribution that we consider, because it's very friendly for the proofs and for how the systems behave, is like a Gaussian-like error distribution like this. So 0 is here in the middle with the highest probability, plus minus 1 of almost that probability, plus minus 2 a little bit less, plus minus 3 a little bit less than that, and it tails off quickly beyond there. Okay, so the parameters we usually think about are a Gaussian-looking error distribution with a standard deviation of about square root n, and that's going to be much, much less than Q. So think of this error as covering basically an alpha fraction of all of ZQ. So centered at 0 kind of has a width of alpha times Q, essentially. Okay, so again, the problem is given these AI-BI pairs with noise in the BIs to find this secret S here. And I'll just mention that, well, let's first write it a little more concisely. So just like we did with SIS, we can bottle up these AIs into a matrix A. So again, the columns of A are just the vectors AI from before, but we also have one more thing, which is basically S times A. Okay, so we basically have a row combination of this A matrix. So if S inner product each of these columns, that's like multiplying S on the left as a row vector. So we have S times A, but there's of course some noise added to every entry of that vector. Rather. Okay, so it's given A and B, find the secret S. Or equivalently, find the errors. Okay, so one observation immediately is that if there were no errors, or if you knew what the errors were, then you could easily solve this problem. This B would be exactly S times A, and then just using linear algebra, you can solve for S, because you know what A is. So it's the errors that make this problem difficult. Oh, okay. Great. That's like refueling a jet. Okay, so good. The errors are what makes this problem difficult. That's the search problem. The decision problem, or decision flavor, is asking you to do something a little more mild, or seemingly more mild, which is simply to just distinguish whether you're given an A-B pair that was created in this way, or whether you were given a uniformly random A-B pair. So in the uniformly random case, there's no secret, there's no errors. B is just a random, uniformly random vector independent of A. Okay, so all you have to do is tell, you're promised to be given either this or this, and you just have to tell with some advantage which of the two you got. Okay, any question about this so far? So just like we have for SIS, we have hard worst case to average case reductions also for LWE. The story is a little more complicated, however. So here's what we have. We can show that search LWE. Okay, so let's go from left to right. There's a reduction from worst case, same two problems, gap SVP or SIVP, to search LWE, where the approximation factor is now like n over alpha. Okay, so alpha being the rate of the noise. So the smaller the fraction of the space that the noise covers, the larger of an approximation you get here. So if you want a harder problem, you should pick a larger rate of noise. That's kind of intuitively makes sense, but this quantifies it. So you get an n over alpha approximation out of if you have an algorithm to solve search LWE. Now, the catch here is that this reduction here is a quantum reduction. Okay? So no matter what kind of algorithm you have for solving search LWE, it transforms into a quantum algorithm for these problems over here. Okay, so even if this is a classical attacker, this becomes a quantum attacker against those problems. If this is a quantum attacker, naturally, this is also a quantum attacker, as you would. But this reduction kind of introduces quantumness into the lattice algorithms. So that's kind of interesting. As far as we know and conjecture, these problems are hard for quantum. And so that still is evidence for the hardness of search LWE. But you might like something more. So we'll talk about that a little bit later. And then there's a second step, which goes from search LWE to decision LWE. So it actually shows that these problems are essentially equivalent via this reduction here. And that actually goes back to a paper by Blum et al. From '93, but just that was for learning parity with noise. It generalizes quite easily to this more general case with a larger modulus Q. And so if search is hard, then decision is hard. And then, assuming that decision is hard, we build crypto systems. So that's the last leap. So most crypto papers will say, assuming LWE, we do blah blah blah, and that's usually the decision LWE assumption they're making. Okay, so that's the kind of picture. It's not the entire picture. There's some alternatives here. So there is also a fully classical reduction from the worst case lattice problem to search LWE. It works for worse parameters and only works for gap SVP. We'll talk about that in the third part of the talk. But it does give you some, it removes quantum from the picture, albeit to a limited amount, a limited degree. And then we'll talk about this more in the next talk where it's more relevant. But there's also a direct reduction, which goes from worst case problems to decision LWE, skipping over entirely this intermediate search problem. And that's still quantum, but it's kind of interesting more in the ring setting, so we'll talk about that more later. So any questions so far about the existing landscape of reductions? I'll do something. Okay, in class, this is a good trick you can try. I require a question. Okay, I won't go on until there's a question.
No,
okay.
If any question. So I'll, this fully classical reduction with worse parameters is still from SIVP?
No. Only from gap SVP. Yeah. So I'll have more to say about that at the end. Okay. So just like for SIS, we can look at LWE as a lattice problem. And it's kind of instructive to see it in this way, I feel. If you don't, then indulge me. But I think it's useful to see it this way. So just like we had the SIS lattice, this defined by like L perp of A, there's also an LWE lattice. And we can define it as follows. So I can call it L of A. And it's basically treating A as a generator matrix for the lattice, so for the code. So this is all the integer vectors that are congruent to S times A for some S. And a nice exercise to show, which you can do in a couple of lines, is that actually this is the dual lattice of the SIS lattice. Okay, it's the dual of L perp A up to a scaling by a factor of Q. So the LWE lattice is actually the dual of the SIS lattice, scaled appropriately. And it's the same argument if you've taken a coding theory class, the dual code, you're given a parity check matrix that defines a code, and then the dual code is generated by that, treating that matrix as a generator matrix. So exactly the same proof of this, which is quite nice. But LWE is now not like a shortest vector problem anymore. It's a bounded distance decoding problem on this LWE lattice. So that is, what we are given is some vector, well, there's some vector S times A here. It's a point in the lattice. But we've perturbed it by adding some noise. And so we're given that perturbed point, so given B, which is close to some S times A, the goal is to find that nearest lattice point. So if you can find V, then basically you can factor out S, or that you've removed the noise, so you can solve for S, solve for the error, and basically you've recovered this lattice point. So that's LWE as a BDD problem. And what's important is that the amount of error that we add is typically very small compared to the minimum distance of this lattice. So there's a unique answer. This B is very close, relatively speaking, very close to some lattice point. It's guaranteed to be, and your goal is to decode it to the unique nearest lattice point. So that's the BDD view of LWE. Or you could say, well, distinguish a B which is very close to the lattice from a uniformly random point in space. That would be the distinguishing or decision problem. So in summary, we have this kind of picture. We have SIS here on the left, which is an average case shortest vector problem. You have the perp lattice, L perp of A. And the goal is to find a non-zero point within a pretty wide radius, a radius where there's lots of solutions on the origin. And in LWE, it's a bounded distance decoding problem on the average, where you're given a point guaranteed to be very close to the lattice, and the goal is to find that unique nearest lattice point. And so, of course, this lattice here is the dual of that lattice. Okay, so any questions about this material? Okay, so I think that concludes part one. Yes, it does. So the last thing I'll say about this is, in Daniele's talk, he showed applications of SIS, which are all like mini crypt primitives. Okay, they all are things you can get generically from one-way functions, and SIS gives you a one-way function. With LWE, this allows us to get into cryptomania. So it lets us build public key encryption and a whole lot of other very fancy things which are also public key encryption type primitives. Okay. So the fact that we have this kind of unique solution seems somehow to be very important for getting like injective one-way functions and public key encryption and things like that. So there's a qualitative kind of change of perspective, or a qualitative threshold that we cross when we go over to the LWE world. So now let's talk about some cryptographic applications of LWE, and along the way we'll have to give some of SIS as well. So not everything here will require LWE, but on the way we will build some things out of SIS as well. Okay, so first an overview. We can build an amazing amount of stuff from LWE. So a lot of kind of cryptographic primitives. All the basic bread and butter public key encryption stuff. So we can build PKE and key exchange. We can build oblivious transfer. We can get, so this up here refers to passively secure or CPA secure public key encryption. We can also get chosen ciphertext secure encryption, CCA secure encryption, with or without random oracles. More recently, we can get pseudorandom functions, or these things called constrained pseudorandom functions that have nice applications. So these are kind of bread and butter things. Then we can get more exotic objects like identity-based encryption with or without random oracles, even make it hierarchical. More recently, it's been shown how to get non-interactive zero-knowledge proofs for all of NP without random oracles, and much more in this category. And then we have things where we couldn't even build them using any previous assumption, like fully homomorphic encryption or attribute-based encryption for very rich access policies. So these are things which are completely new, or were completely new at the time they were built, to the field of crypto. But now, we can build them from LWE or Lattices, and that's more or less still the only thing we know how to build them from, which is pretty cool. So that's a brief sampling. These are the things, all of these things are what I'll cover for the next 40 minutes or so. We'll do all of these. Okay, we'll do a couple of these. Yeah, you bought it. You bought it. We can do it. Okay. So let's just do a couple of these. The most basic one is public key encryption. So this is you can't do any of these other things without knowing the public key encryption scheme. So this is the most basic thing that everything else is based upon. Okay. So this was given in Regov's original work, although we're introducing a twist from GPV in how we're describing it for a reason that'll be useful. Okay, so here's the public key encryption. First, we're going to choose this matrix A, and you can think of it as the receiver chooses it in key generation, or you can think of it as it's used by everybody, right? So some trusted party picks a random A, and everybody uses it. Okay, either way you like, this will work. Okay, so Alice here is the receiver, and so she's going to generate a public-private key pair. Her private key is just a short vector x, a short integer vector x. And her public key is just a times x. So we just apply the SIS hash function, basically, to Alice's secret key to get her public key. And one fact that you can prove using a well-known lemma called the leftover hash lemma is that the public key is uniformly random if the parameters are set properly. Okay, so if this matrix A is wide enough, it was shaped like this, and we have n rows, and if you have much more than n log q columns, then Alice's public key is just a uniformly random vector. Good. So that's her public key and her private key. And now Bob comes along and he wants to encrypt a message to Alice. Let's say he just wants to encrypt a single bit. So single bit encryption is sufficient. It's complete. So here, what he will do is basically create an LWE vector. Okay, so he's going to pick an LWE secret S, and he's going to do S times A, but add some error to it. And notice that this doesn't have anything to do with Alice's public key. So he can do this kind of in advance or whatever. He doesn't need to use Alice's public key for this. But then after the preamble, he actually writes, he also takes S times Alice's public key. Okay, so he's got S times A plus noise, and S times U, the public key, plus some noise as well. And then he does this curious thing where the bit he wants to encrypt, the message bit, he adds either 0 times q over 2 or 1 times q over 2. So basically, to send a 0, this is just S times U plus error. To send a 1, it's S times U plus error, but then flipped to the opposite side of the ZQ cycle. OK, so that's the payload, which carries the message bit. And he sends both of these things to Alice. Now, how does Alice decrypt? Anybody see it? I'll leave it as an exercise. All right, so Alice has to use her short secret key to decrypt here. What can we do?
The key by x?
Yeah, multiplies the key x by this here. Yeah. So imagine take this term here and multiply by x on the right, right? And what you get is S times A times x. Well, that's S times U. And then you get E times x as well. Now, so you're going to get S times U plus something small. It'll be E times x. E times x is small. And this also is S times U plus something small. So these you can subtract to cancel them out. Okay, so what Alice will do is take this B prime minus this B times x. And if you do the calculation that we just did, what you end up with is this term here carries through. This term here essentially cancels out with B times x, except there is an E times x and a little E prime carried through. Okay? But the key point is that E and x are both short. E is a short error, x is a short vector. So E times x is pretty small. And if you set up the parameters correctly, E times x is much smaller than q over 2. So essentially, Alice is going to get the bit times q over 2 plus some error, which is not very significant compared to this. So this is either 0 or q over 2. It's a little bit perturbed by error, but you can just see which it's closest to, and that tells you the message bit. Is that part clear? Just write it here for reference. So these cancel out, and we're left with E prime minus EX. These are both small, and so if these are much smaller than Q over 2, you can recover the bit here. Okay. So that's why it works. This is why you can decrypt using your knowledge of X. Now let's look at security. Okay, so suppose there's some eavesdropper, and the eavesdropper gets to see all the stuff that's public, sent over the channel. So the eavesdropper knows the matrix A, the public key U, and then these two components of the public key. So the thing to notice is that let's look at this B prime. compared to A and U, right? So A and U is really just a uniformly random stuff. A was picked uniformly, and then U is also uniform by our choice of parameters. So this is just like a uniformly random matrix. And this vector here is basically S times, multiplying S on the left by these two things. Right? S times A and S times U, that's what B and B prime are, with error. So if you just ignore this part here, these two things here by the LWE assumption are pseudorandom. Right? So they look to the attacker like truly uniformly random a vector B and B prime. Okay, so that's completely, and if we replace these red B and B prime with truly uniform ones, then those hide the bit information theoretically. So that just perfectly hides the bit. So by switching the ciphertext to have this form, now the bit is perfectly hidden. So that's like the one-line proof of security for this crypto system, or at least CPA security. Any question about this so far?
Can you remind us what's the difference between this scheme and regivs?
Yeah. So okay, great question. So what's the difference between this and regivs? The roles are basically reversed. In regiv scheme, this part is Bob. So Bob has the public-private key. This part is Bob's public key, and this part is Bob's secret key. And then this is part of the ciphertext, and well, this is computed differently by Alice. Okay. So if you squint at this and look at it in the right perspective, what's basically going on here is a Diffie-Hellman type key exchange, where this part is like Alice's message, this part is Bob's message, and they are both able to compute something close to S times A times X. So using their respective secrets, they can get something like S times A times X with some noise. That is what acts as the Diffie-Hellman shared key. So that's just kind of rearranging how you look at this. Okay, so that's the public key crypto. All LWE-based encryption has this at the core of it. There's, as far as I know, no other way to do public key encryption with LWE. Yeah.
If you wanted to make A square, would you add error to U?
Yeah, exactly. So there's a paper by Richard Linder and myself following on an idea from Lubashevsky, Palacio, and Segev, which uses a square matrix A. This U is AX plus error. And this is also S times A plus error. You have to be careful. The S then is not uniformly random, but it also comes from the error distribution. And it turns out that that is safe to do. So the S can be drawn from the error distribution without losing any security at all. So with a couple modifications, you can make A square. Yeah.
Another way to encrypt from LW is to build a trapdoor one-way function. So
Yeah.
the trapdoor, you do LW as a one-way function.
Right. It's
Called this.
it's kind of the same, right? The sender is still sending this, and then.
Decrypt in the same way.
Yeah. Well, okay, that one degenerates to this one, I guess.
If you have one vector in the trapdoor.
Yeah, if you have one vector in the trapdoor, that's all you need to decrypt. So I kind of see it as the same thing. Well, I guess a more powerful version of it. Yeah. Okay, so those are some variations of public key encryption you can do, but you know, they're all basically morally the same, working in the same. Okay, so for a second application, what I would like to talk about is digital signatures. For signatures, all we need actually is SIS. This is going to be different from Daniele, I think, showed the one-time signature and then kind of put that into the tree-based framework. We're going to give a different kind of digital signature scheme here, which is a many-time scheme. So here's how it works at a high level, and I'm going to steal a little bit from Shweta's talk, I think tomorrow, right? Or maybe Friday. So I'll give a little preview. Shweta will give many more details on these kinds of techniques. But here's the main idea. Okay, so digital signature scheme, we have a signer who should create a verification key and a signing key. So the verification key is just a random matrix A, as always. But this is created in a clever way together with what's known as a trapdoor T. We'll call it T for this matrix A. So I won't tell you, well, I won't tell you yet exactly what form this trapdoor takes, but I will tell you what it allows you to do. So there's some special strong trapdoor here. And here's how we're going to sign messages. Okay? So to sign a message mu, you use the trapdoor in the following way. We are going to, first thing we do is we hash the message, let's say using a random oracle, into ZQN. So we take the message, which might be like, hi Bob, how are you today? We apply a random oracle. That gives us a random vector in ZQN. And then the signature that we put out for that message is a randomly sampled short solution to AX equals the hash of the message. Okay, so how do we do this? I'll tell you in a moment, but this is the idea. Right? So we're going to sample a short solution to this equation here. To be a little more precise, what we need to do is to draw the signature X from a distribution which doesn't reveal information about the trapdoor. Okay? So this is going to be some kind of oblivious sampling algorithm. And concretely, what we will do is draw X from a Gaussian distribution. So there's a whole set of solutions to this equation. There's lots of short vectors X that satisfy this equation. And we're going to randomly choose one according to a Gaussian distribution. Okay, so all of these represent the various solutions. We're going to choose one from this distribution here, which is Gaussian shaped. But it's only over the solutions X to that equation. Okay, and what's important is that this distribution is kind of independent or oblivious to the shape of T. So it reveals no information about T. It's just a Gaussian distribution. Okay, so let's see how someone can verify such a signature and why this signature scheme is secure. So to verify the signature, the verifier has the public key A, the message itself, and some candidate signature. And what the verifier does is just hashes the message as before. Okay, so you get this random oracle applied to the message, and then we just check that AX equals the hash of the message. Okay. That's the first thing we check. And then we also check that X is sufficiently short. So it should be a short enough solution to this equation here. Okay. And if so, then we accept the signature as legitimate. Otherwise, we will reject. Okay. So is it clear how signing and verifying work essentially here? Well, let's now look at the security of this. And it's just a very high-level idea of why this is secure. So for security, in order to forge a signature for a message, so suppose the forger wants to sign, produce a good-looking signature for this mu star, then what the forger has to do is to actually find a short vector x star such that ax star equals the hash of mu star. But this is exactly the SIS problem. Okay. The random oracle hashes the message to a random vector u. So we're really just saying, OK, find me a short solution to ax star equals random vector u. Right? And that is the SIS problem. Well, OK, it's the ISIS problem, I guess. The same problem. OK, so this is why, informally it's hard to find a signature. Of course, in the signature forging game, you actually have access to a signing oracle, which can potentially help you produce this forgery. And intuitively, the signing oracle is producing signatures from this distribution, and this is kind of a zero-knowledge distribution that doesn't help you. Okay? So you have to do the proof, of course, in the random oracle model, but intuitively, seeing a bunch of signatures just gives you a bunch of random vectors from Gaussian distributions, which you could essentially generate yourself. So that's the high-level security argument for this. Let me take a question about this.
So what is exactly this trapdoor doing, or how do you construct it?
Yeah, so like the trapdoor is magic, right? I haven't told you how to do what it looks like or how to do these things. I'll do it on the next slide. But yeah, for now, just assume there's a trapdoor which allows you to do this operation here.
So what is exactly what it allows you?
What's that?
Exactly what it allows you?
So good. It allows you to sample from a Gaussian distribution over the solutions to this equation. And I'll show you imminently how that actually works. Any other question? Okay, so as an exercise, break this scheme. I lied a little bit. It's not secure. You can break it. You need a little tweak to avoid it breaking spectacularly. Okay, but it's a small tweak. Yes.
Okay, so
Not you. Okay, don't spoil it. Yeah, yeah.
do you actually break it, or you show that the proof doesn't work?
You can. I think you can. I think you can break it. Yeah. But unless the parameters are extremely tight, and I think you can break it.
So does that mean that there's something that you've told us here that isn't correct?
Something I've told you is not complete, I guess.
Will you give us a hint?
I'll give you a hint. So this random oracle of mu, the way to fix the problem, which I won't tell you, is to add some randomization to the hashing. Okay, so when you hash mu, actually choose some random salt along with mu, and hash mu and the salt together, and then include the salt in the signature. So with a vaguely enough defined operation here, it's okay, but okay. So that's the, oh yeah, question here.
This was a many times scheme, so
Yes.
is there something to do with if you use A multiple times or if you
Good, yeah, so it's claimed to be a many-time scheme. That is, you can sign basically an unlimited number of messages. The attack I have in mind is related to the many-time. It doesn't really have, I suppose it has to do with the fact that A is used, it's the same A through all the signatures. There's a specific kind of many-time signature query that you should issue to help you break this thing.
I guess not to spoil it, but if you generate the signature deterministically.
But I didn't. I sample from this.
I know, but between friends.
Okay. So yeah, many time is another hint. Okay, so let me tell you a little bit more about how to implement this operation here. So again, the goal is we have a trapdoor which has some form I'll tell you about, and the goal is to sample Gaussian distributed solution to this equation here. So okay, good, I wrote it here. So again, the goal is sample an x such that ax equals some target vector u, and the trapdoor that we will have is going to be a particularly short basis t of our lattice. Okay? So we have the SIS lattice, and what one can do is to actually generate an SIS lattice, or a random matrix A, together with a short basis of that lattice. Okay? So the signing key that Alice knows is itself a basis made up of short lattice vectors, okay, a complete basis of the lattice. Okay, and in particular, let's say there's some upper bound on the length of the basis vectors. Okay? That upper bound will be the standard deviation of our Gaussian. So again, the advantage of this is that this distribution we're sampling from actually doesn't leak any information about the basis itself, like what its geometry is. The upper bound on the basis vector basis vector lengths will be known. So that's a public value, but nothing more than that is known about the, or is leaked about the basis. Okay, so here's how to do it. The algorithm is rather simple to describe pictorially, more work to do formally. But the idea is to run the nearest plane algorithm. Did you do the nearest plane algorithm? No? Okay.
There was one line.
One line, okay.
Yes.
Yeah,
But,
okay. Okay, good. So nearest plane algorithm, but with some randomized rounding instead of deterministic rounding. Okay, so here's the idea. We have the coset L perp of A with coset U, and we want to draw from this distribution here, right? So we have the shifted lattice, and let's say we have these vectors T1 and T2, which are a basis of the unshifted lattice, right? So if I were to put the lattice at the origin, these vectors would generate that lattice. Okay, but we want to sample from this shifted lattice under a Gaussian distribution. So here's the approach. It's an iterative algorithm. What we do is imagine partitioning the coset according to the multiple of T2. Okay. So we kind of have a plane and another plane and another plane and another plane, where within each plane they have the same multiple of T2. But arbitrary multiple of T1. Okay, and then we, in the nearest plane algorithm, what you would do is just start at the origin and round off to the nearest plane. That's where the name comes from. But we will round off to a randomly chosen plane with a certain probability. Okay. So the most likely plane we choose would be this one, which is closest to the origin, but maybe by chance we happen to choose this plane instead. So we pick a plane at random, which is near the origin, and then we project from the origin orthogonally onto the plane, and then we just iterate. So for iteration, well, there's only 2 dimensions here. So when we iterate, now it's a matter of rounding off within this plane to a nearby lattice point, or a nearby coset point. So maybe we randomly round off to this point here. So if you do n, in general, in n dimensions, you would do n stages of rounding to a nearby plane, and then working within that subspace and doing it again and again and again until you end up at a point. Okay, so that's the algorithm, essentially. Just round off to a nearby randomly chosen plane each time. And what's remarkable is that this actually does, for the proper parameters, sample from this nice, clean Gaussian distribution. I'll give just the highest 3-line summary of the proof. If you look at this distribution over here, and you look at the total probability mass assigned to each of these planes, okay, it turns out that the amount of the probability mass assigned to each of these planes is depending only on the distance from the origin to the plane, the orthogonal distance. So it doesn't matter how the points are shifted within each plane. There's essentially a smoothing argument which shows that the probability mass basically only depends on the distance of the plane from the origin. Okay, and so what that means is that if you round off to each plane with the appropriate probability, which depends only on the distance to the plane, then you are kind of sampling from the right distribution. We're sampling from the right marginal distribution at each step, and then overall the final output has the correct distribution in the end. Okay, so that's a 3-line proof encapsulating the key idea of the analysis. Okay, so any question about that? Yes?
Do you need here something like that the basis T has roughly orthogonal elements, or it's not important?
No, yeah, the angles between the basis vectors is irrelevant. All that matters is that the Gram-Schmidt vectors, actually, of the basis are smaller than the standard deviation of this distribution here. So I wrote that the vectors themselves are shorter than the standard deviation, but in fact, the Gram-Schmidt lengths are all that matter. So yeah, any 2 bases that satisfy this bound will generate the same distribution in the end. And that's what I mean by the output distribution doesn't leak anything about that basis.
Almost the same.
Essentially, up to tiny statistical error. Yeah. Good question. Any other question about this thing? So I'll just mention, I think Shweta will probably, on Friday, talk about other ideas. This is not the only sampling algorithm. This is not the only notion of a trapdoor. You don't have to use a basis necessarily. So there's other ways to accomplish this same goal, which you can then plug into signature scheme, from the previous slide. Okay, so that's how we can get signature schemes from SIS. But it turns out that there's a lot more that we can get from this technique here, this kind of oblivious Gaussian sampling. And one thing that we can get to give away the punchline a little bit is something called identity-based encryption. So this was a concept proposed by Shamir in 1984, who identified the issue that when you do public key encryption, you have to get the receiver's public key. You have to know it belongs to them. Right? And so to answer this, we've built the foolproof, airtight, public key infrastructure, right? Which has never gone wrong. This is an alternative to like the public key infrastructure. So Shamir says, suppose that there was a way to generate a public key and a secret key, or these are called the master public key and master secret key. And then you can have many different user-specific public and private keys underneath this domain here. So that is, if we could have many users, there's Alice and Bobby and Carol here, and the central authority generates their secret keys for them. Okay. So their secret keys are produced by the authority, and they don't have public keys. Well, or their public keys are their names. They have the name or the email address or something like that. So if you want to encrypt a message to Alice, for example, you don't need Alice's public key. You just need the master public key and then Alice's name, and you can encrypt a message to her. And you could do the same with Bobby and Carol. You can encrypt messages to each of them individually using only their name. And the advantage of this, of course, is that you don't need a public key for each of the people in the world. You just need the one master public key. And you need to know the name of the person you're trying to encrypt. Naturally, Alice can decrypt this message, but the idea is that Bobby and Carol should not be able to read the message, this ciphertext. And one way we can formalize that is to say that if Bobby and Carol actually were adversarial and even combined their secret keys together, they used all the secret knowledge that they have, they still can't violate Alice's privacy. Still can't read her email. Okay? So that's kind of the informal requirements of a identity-based encryption scheme. And for a long time, it was not known how to build it. So that changed in 2001. Bonet and Franklin gave an IBE based on this kind of new math, or at least new math for cryptography, these bilinear pairings. And then it came out that, I guess a few years before, Clifford Cox built an IBE based on quadratic residuosity. It was the same guy who invented RSA before RSA did, so good job. And then with the stuff that we've seen so far, we can do it with lattices as well. So here's the picture. Actually, we've done everything we need to get identity-based encryption. It's all in this picture. So if you remember the public key encryption scheme from before, it looked a lot like this. But now, what is the difference? Alice doesn't choose her own public and private key. They're kind of chosen for her. Or more specifically, the authority generates Alice's secret key for her, and she has no public key, she just has a name. So let's see how this works. The master public key is this matrix A, and the master secret key is the same trapdoor T that we used for the signature scheme. And now, again, instead of Alice picking her own secret key, the authority chooses it for her. Specifically, it's going to choose a Gaussian X such that AX equals, well, the hash of her name. So instead of having like, well, I guess you could consider this as her public key, but it's kind of corresponds to her name, right? Anybody can map her name to her public key. So by hashing her name, you get her public key U, or her identity public key. And then her secret key is just a short x such that AX equals U. So what's important here is the relationship between Alice's private and public key is exactly as before. Okay? You can imagine that x is just this short vector, and her public key is a times x. That was exactly how the public key encryption scheme worked before. It's just we're kind of choosing them in a reverse way. First, we hash her name to get her public key, and then the authority samples the corresponding secret key for it. So that's it. Everything else is identical. The encryption works just as before. So Bob, if he wants to encrypt a message to Alice, well, he can hash her name to get her public key on his own, and then do everything as before. Okay, just encrypt in this way as before. So, any question about this? Yes.
If for signatures you needed salting, how
Yeah.
avoid the need for salting here?
Good. Yeah. So that the salting idea, good observation, does not work here because then it's not clear what salt Bob should use. So the other thing to do is the one that the node spoiled, which is to do a deterministic sampling. That is one way to go about this, where you use like a pseudo-random function as your source of randomness when you do this sampling. It's a different way to go about it. Or you can do something like only give Alice her key once in her life. Okay. So I don't know if you want to do that, but that's one solution as well.
If I'm an attacker, can I hash, say, Alice's name and ask the centralized provider to give me the sample?
Great. Yeah. Yeah. So what this whole like identity-based encryption ecosystem relies on, the authority only gives Alice's secret key to Alice. Right. Alice has to show that I'm really Alice and I'm not Carol. Right. If you could impersonate somebody and steal their secret key from the authority, that's obviously a problem. Yeah. So we should imagine here that only Alice knows this X. Bobby, will get a different hash, and so we'll get a different X prime or something completely different, independent from Alice's secret key. Yeah, that's a good point. Other questions or concerns, remarks about this one? Okay, so this is just a flavor, a tasting of what we can do with LWE, and tomorrow and Friday there'll be much more building on these kinds of constructions and ideas. So for the remainder of the time, what I'd like to do is give an idea of the worst case, average case reductions for LWE, and these are going to they're kind of souped up versions of what Daniele showed in the talk this morning, with new elements to them, and accounting for the nature of LWE as a bounded distance decoding problem. So let's just recall what we know about LWE. This is the state-of-the-art picture of the reductions. Worst case lattice problems on the left, quantumly reducing to search and then decision LWE. Also a classical reduction with worse parameters and problems, and then this will be later. So what all these results have in common is a core component, which works as follows. It's basically a way of turning a BDD instance on an arbitrary lattice, so a worst case BDD instance, into LWE samples. So there's a machine basically which kind of randomizes a BDD instance into LWE samples. So here are the two pieces of input that this component requires. So what I first need is a BDD target. And what I mean by this is we're talking about bounded distance decoding on a lattice L to within distance D. Okay, so what I mean here is that there's a target vector t, and it's within distance d of this lattice L. Okay, and this is just some arbitrary worst case lattice. So t is close to v, with at least it's within distance d of a vector in the lattice. And then the second input to this component is many discrete Gaussian samples. Okay, so still this picture, oops, yeah, so this distribution, I have, I want to take many, I want to be given many samples from this distribution where the width of the distribution is roughly r over d. Oh, and this distribution is over the dual lattice. Okay. So we have one target, many such Gaussian samples, and notice that the dependence on d here, so the width of the Gaussian is inversely proportional to the BDD distance. And what this component does is, given these two kinds of inputs, it's going to generate LWE samples. The LWE samples will have a secret S that basically corresponds to the closest vector, or the solution to BDD. So the secret S basically is I'm lying a little bit in one-to-one correspondence to the vector V of the BDD solution. And the amount of error in these LWE samples is basically R. That is, it's the product of the distance bound and the Gaussian width, the width of the Gaussian. So d times r over d is r. Okay, so why is this interesting? It's very interesting. The first thing is that if you had a LWE solver, right, if you had an oracle which takes these LWE samples and tells you what S is, well, then that's basically telling you what V is. So it's solving BDD for you. So you can take your BDD instance, run it through this machine, get LWE samples, solve LWE, and then that tells you what the original BDD solution was. So that's why this is a useful reduction. And indeed, it's worst case to average case. This lattice is arbitrary, but these are legitimate, properly distributed LWE samples. Okay, so that's the core component. Everything on this page uses that as the heart, but then builds things differently around it. Okay. So let me first tell you about Regev's original iterative quantum reduction. It's very nice. Let's suppose that we start with, well, not just suppose that we will start with, the goal would be to solve BDD to a very tiny distance. Okay, so some distance d, which is really, really much smaller than the minimum distance of the lattice. Okay, so our goal is to solve BDD to this tiny radius. Well, we put it through the machine, the core component that I just told you about, right? So if I've got what I need, then it suffices to have really wide Gaussian samples over the dual lattice. And then my machine can produce LWE samples. Given a target here and a bunch of samples from this, we get LWE samples. We can invoke our LWE oracle, and that solves BDD for us. So with a very wide Gaussian, I can solve BDD to a very tiny radius. Good. Now here's the really cool idea, or one more really cool idea, is to say, well, if you can solve BDD to this tiny radius, it turns out you can quantumly generate samples from a slightly narrower discrete Gaussian. So there's a quantum step which will say solving BDD to this radius gets you, allows you to generate discrete Gaussian samples from a narrower radius. Now this is narrower than that, and so if this is narrower than that, what does that allow me to do? Well, it allows me to solve BDD to a slightly wider radius. So let's do it again. Right? Let's say, okay, now if I have a BDD to a slightly larger distance, I can combine it with these narrower samples, and then using my LWE solver still solve BDD here. Make sense? I'm doing something pretty fancy and subtle here. But we can repeat this. Okay. Being able to solve BDD to this larger radius lets me generate even narrower discrete Gaussian samples in a quantum way. And so that lets me solve BDD to an even larger radius up top, and I can just go back and forth iterating this. Eventually, it stops working. It stops working when these samples get so narrow that they actually suffice to solve SIVP and gap SVP. So being able to generate very narrow Gaussian samples is more than you need to handle these problems. So this is the structure of Regev's quantum reduction. Very nice. Just going back and forth between BDD and sampling, using one to solve the other better, and repeating until you get something very good at the end. Okay, but this is quantum. The natural, yes, question here.
The first one?
Yeah.
At some point you have to solve something efficiently, right?
Great, okay. So yeah, maybe the question is like, where did these come from, right? Like, where did the first samples come from? Very good, yeah. So at a very wide radius, like an exponentially large radius, you can generate these yourself. For example, using the algorithm I showed with a really bad basis. Okay, so yeah, that's very important. Yeah, so this thing gets kicked off just by, you can do it yourself. And then these, you need the solver to generate furthermore.
So these red points are in the lattice that was given to you as input at the beginning?
Yes, yeah, these are all over the original L star here.
And this SIVP and gap SVP are solved in this lattice or the dual?
Well, this is over the L star, and this one's over L. So decide which problem you want to answer, and then define L and L star accordingly. Okay. Yes.
Can you give some intuition why BDD with the quantum computer
Yes.
narrow Gaussian?
Right, yeah, so good. So why does solving BDD to this radius allow you to generate samples of this form here, right? So the rough answer is that solving BDD to this radius allows you to generate a quantum superposition, which you can think of as like tiny little Gaussians centered at these lattice points. So imagine just very spread out, widely spread out narrow Gaussians centered at all these lattice points. And if you take the Fourier transform of that superposition, it ends up being corresponding to this distribution here.
This step involves a quantum Fourier transform.
Exactly, yes. So this step here, from here to here, is a QFT. Yeah.
So the quantum superposition you can generate anyway. What BDD is useful for modular reduction. But you want
No, the opposite. So
it's for modular reduction to be invertible.
to be non-invertible. So you can generate a superposition of these peaks, but there's some extra junk correlated to it. There's an extra register with junk correlated to it, and you need to get rid of that junk.
Okay, different way to think. I mean, you can think of generate a random superposition for just a noise vector.
You can do that for sure, yes. Yes.
No classical, I mean,
Wow.
without.
Okay, right, without BDD, yeah.
Then you use that to make reducing this peak modulo the lattice. You want to do that quantumly, and for that you need it to be invertible.
Maybe to generate this. Yeah, to generate. I'll have more on the next slide, so that will probably help. Okay, so yeah, so the question is like, why quantum? Where is quantum being used here? So the obvious answer that I just gave is in this iterative step, right? So being able to solve BDD allows you to generate these samples that uses the quantum Fourier transform in a essential way. It'd be great if we could do this step without quantum, but we have no idea how to. Here's maybe a slightly better answer, more detailed answer at least, is to actually be able to usefully employ the BDD oracle. Okay, so this is I think what Daniele was just referring to. How can we create this superposition here? Well, you can choose some V, and then you're going to add some error to it. And then you could think of like invoking the BDD oracle on T. Right? And what do you get back?
V.
V, right? You get back V. You already knew V. You chose V yourself to start with. It's right there. Right? So the oracle is telling you something you already knew. Seems like it's useless. Right? It's kind of a zero-knowledge oracle, I guess, for you. It's telling you something you already knew. So how could this oracle be useful? But the point is that in the quantum realm, the quantum can uncompute V. Okay, so when you invoke the oracle, you get back V, and you can use it to uncompute or forget that you started with V. And this idea is used to produce this superposition.
Do you start with a superposition of the lattice points, or just...
No, we want to generate such a superposition. That is, we want to generate a superposition of Gaussians centered at lattice points.
Okay.
You're saying, like, what's the random lattice point? Like, what's the idea of starting at an arbitrary lattice point V?
Yeah, okay, so you can work modulo the lattice and not have a V in the picture at all, but that's some, like, I don't know, advanced lattice stuff.
I covered this a little bit.
You covered it yesterday, okay. Yeah, okay, good. So instead of choosing a V, just start with the perturbation and then reduce it mod the lattice. But then you have to forget the amount you shifted it by when you did this reduction. Well, how do you forget it? You invoke the oracle to tell you what it was and then uncompute it. It's pretty mysterious stuff, but that's quantum. Okay, so once you forget V, then you have the superposition you like, and you can do a QFT to generate these points. Okay. So that's the Y quantum, but maybe you don't like quantum, or maybe you don't want a quantum reduction, you prefer a classical reduction. So here's one way to avoid the quantum. It doesn't entirely resolve, it doesn't give you everything that the quantum reduction gives you, but it gives you something. So the key idea is there's an alternative way of solving just gap SVP. It doesn't work for SIVP, but it does work for gap SVP. So here's the usual picture. You start with V, you add some perturbation, you invoke the oracle, it tells you V, something you already knew. So that seems useless, but imagine as a thought experiment a different world where your lattice now looks like this. So the lattice is kind of maybe dense in a certain direction, or it has a small minimum distance. So imagine doing the exact same process on a lattice that has such a small minimum distance. You start with V, you add some T, you invoke the oracle. What does it tell you? What does it tell you? Well, the key insight here is that this is actually, there's a few things wrong with this. This doesn't make any sense. This is an illegal BDD instance. We're perturbing T by much more than the minimum distance of the lattice. This is going to create an incorrect, bizarre, unknown LWE distribution when we run it through the reduction. The samples won't look proper at all, but doesn't matter. Doesn't matter. Who cares? The point is that if your minimum distance is much less than D, the oracle simply cannot guess the original vector. Okay? There's some ambiguity about where you started. Did you start here, or did you start here to get T? So the idea is that on the normal case, the usual world where the minimum distance is large, the oracle will return V. But in this world where the minimum distance is small, the oracle provably cannot return V, or at least can't always return V. It has some probability of not returning V. And so this actually allows us to distinguish the case of a large minimum distance from a small minimum distance. That's exactly the gap SVB problem. So that's at least the kind of the core idea. There's a lot of, oh, I should mention, this actually can be viewed as a, if you know the Goldreich-Goldwasser proof system, can be viewed as some kind of version of that between the reduction and an oracle. So I'll just mention there's some technical obstructions to making this work. For example, hey, where do we get the Gaussian samples from? You need those to run the reduction. We don't have quantum, so we can't generate them quantumly. But you can do that if you have some basis for L star, you can run the sampling algorithm. So depending on how good your basis is, the modulus will be essentially equal to that. And for example, you can use an LLL reduced basis. That's a 2 to the n good basis. So your modulus is exponential. So this is what I was referring to with like worse parameters. This kind of only works with an exponentially large modulus unless you assume some better basis is available to you. And also, this is a one-shot thing. It's non-iterative, and it doesn't work for SIVP in particular. So it distinguishes small minimum distance from large, but it doesn't actually find short vectors like the quantum algorithm does.
So here, non-interactive is better than interactive, really.
Yeah, I mean, I suppose this non-iterative maybe is an advantage, but it comes with these prices. Yeah. So I view it as maybe a disadvantage, or at least its implications are a disadvantage. Okay, search decision equivalence is also an issue you have to get over because previously this was only proved for polynomial moduli, and this is an exponentially large modulus. You can get around this by using a smooth Q and Gaussian error. So this is maybe another exercise. If you break the decision, if you break the digital signature scheme, then work on this. Okay. Or, as we'll say in the next talk, you can just reduce directly to decision without using search as an intermediate problem. And that's an alternative thing you could do in this setup. Okay. So this basically addresses all the technical things that come up when you try to use this approach. Any question about this? So I was asked to talk about open problems. So I'll tell you my 4 favorite LWE open problems. They're in decreasing order of difficulty, maybe, although who knows, right? Okay, so the first one is to actually get a fully dequantized worst case hardness proof for LWE. So get something which works for the same parameters as the quantum reduction, also works for SIVP, the whole ball of wax without any sacrifices. That would be fantastic. I don't think anybody has any idea how to do that yet. But it would be great. Okay, then the next 2 are about applications. So one thing that I mentioned in applications is that we can do fully homomorphic encryption from LWE. But to get really fully homomorphic encryption, that is with no bound on the what you can evaluate homomorphically, you need a circular security assumption so far. So this is a big problem, like get unbounded FHE without any circular security assumption. Just to get from plain LWE. That's a big interesting problem. Okay, here's a problem I'll put on the whiteboard up on the 2nd floor once it's properly formalized. Okay, and it'll be worth $15. Yep. $15 can be yours for solving this problem. So I would like an adaptively secure IBE without random oracles, but has the same efficiency as the scheme in the random oracle model. So the random oracle model scheme is adaptively secure. I want one without random oracles, but without giving up efficiency. In fact, we can do this in the standard model. Shweta will talk about this. We can do it in the standard model, but only for a weaker selective security notion. Okay, so also getting adaptive security, I think we don't know how to do this yet. And then a 4th problem has to do with something I didn't even define, but it's a nice question, I think. So there's LWE, and then there's something called LWR. The R stands for rounding. And the idea is, instead of adding random like Gaussian errors, you just round off. Round off to the nearest multiple of 10 or something like that. So it's a way of like making the errors deterministic. And we have some hardness proofs for this problem, this learning with rounding, but they're not very good. They're much weaker than what we know for LWE. And LWR is a nice problem. Maybe there's good hardness results. Maybe there are actually better algorithms for it. We also don't know any algorithms that perform appreciably better than for random error. But I think this is a really interesting direction that hasn't been really looked at enough. So that would be a great problem to work on. Okay. So happy to chat more about these problems over the next few weeks. That's all I have. Thank you. Any last questions? Yes.
This dequantization.
Yes.
So your work was like as a blow up, an exponential blow up.
Yeah, for the modulus has to be exponential, and it does not work for SIVP.
Oh yeah. So but there's nothing in between. There's no classical reduction with a little bit better than that.
Well, not for the standard like gap SVP problem as usually defined. As I mentioned, there's this notion of if you're given a zeta good basis. So if you're given a basis that's like better than an LLL reduced one, you can get a better parameter Q. But this is a little bit of a non-standard kind of problem. So investigate that problem more would also be a very useful thing to do.
So Chris, BLPRS does make Q smaller, right? So really the problem is SIVP.
For which? BLPRS makes Q smaller at the expense of making N bigger. And N log Q remains the same. So it actually doesn't improve the parameters at all. It just makes the parameters more, I don't know, more palatable. I don't know. That's good. They look nicer, yeah, maybe.
Good.
But it doesn't actually improve the parameters.
And the error is much worse, right?
And error, well, worse in which way? Yeah, the error rate, I think, remains the same, roughly the same. Yeah. And so the rates, these, whether it's classical or quantum, they have basically the same behavior in terms of error rate of LWE and how that translates to an approximation factor. So that we can't expect to improve, or there's nothing to improve there, classical versus quantum, but other parameters could be improved. Okay. Thanks again for your attention.